Hi. Now, as an application of the quantization method that we have just shown in the previous video, let us apply it to find the Schrödinger equation in some orthogonal curvilinear coordinate system. We will be trying to find it in spherical coordinates, but of course the method can be extended to any orthogonal curvilinear coordinate system. Okay, let's begin. We have now constraint, one constraint. We may use only the axioms. We are not free to introduce anything else. Note that in general, quantum mechanics, in usual courses of quantum mechanics, what you do is to write the Schrödinger equation in Cartesian coordinates. You then have the equation expressed in terms of operators, and the kinetic energy operator, you then express it in the coordinate system you want. Then, for instance, spherical coordinates. Then you have the equation written in the coordinate system you want to. But we are not free to do that in this kind of approach, an axiomatic approach. If the axioms are sound, they must reflect this by showing that if you write the axioms in the desired coordinate system, you naturally get the Schrödinger equation in the same coordinate system by simply repeating the same steps of the quantization method. Let's see if this is the case. Okay, the first thing to do is to write the first axiom in the coordinate system we want. Here it is written in spherical coordinates, of course, in both in the configuration and the momentum space, phase space, which is here written also in the same coordinate system, but only expressed in terms of vectors. The second axiom is the integrated Liouville equation, which is now written in terms of the desired coordinate system. If we do that, then this derivative must be written explicitly in terms of the new variables as in this expression here. So, of course, as expected, the introduction of this new coordinate system makes things a little bit harder. But in any case, we may be able to see that if we make the same step of multiplying this equation by the kernel and integrate it in the volume on momentum space, then this equation can be easily taken into this equation for the variable z, exactly as in the previous video in Cartesian coordinates. Okay, this is the first step. The second step is to obtain the expression for z in terms of the psi's, as we have already done in the last video. This is of course much more complicated, and we get this expression here. Now, obviously, the step we have to do is to substitute dz into this equation and find the equations related to R and S. R and S, which are the new variables introduced when we write psi in terms of these equations. Now we already write it in terms of Planck's constant. Okay? We must show these in fact two equations appear. This equation we must notice that is an equation related to a scalar product. In general, in fact, this equation comes multiplied by r squared, but since it will be equal to 0, it doesn't make much difference. So this is the zero order, and this is the first order equation. But we have to get this equation. We just showing what we expect here. If we got this equation, then this equation will be equivalent to the Schrödinger equation. Of course, these calculations are very hard to do. So we will, for the moment, change to an algebraic computation program to make them, because otherwise it will be long and difficult to get. Let's go. We are now here in Maple program. I have written a program to get the same results that were presented in the previous sections, and I'm trying to get them explicit here. So let's write the dx, dy, and dz, and also dpr, dpx, and dpz in terms of the new coordinate system. This is the way we get the first dx, dy, and dz in terms of the new system variables. The same with px, p theta, and p phi. And now we can show that we get by simply making the product between p's and dx, which is the dq now in the desired coordinate system. We simply get this. This is natural to get, and it will be true for any orthogonal curvilinear system, because this kind of transformation is the so-called Mathieu canonical transformation, and Mathieu canonical transformations have this property. In any case, we may now write the equation that we expect the function z to satisfy. We have just seen it in the presentation. So this equation is this one, and it is written as a procedure. So it is expecting the function zq. We may write these operators in terms of the new variables. Here we are writing them here, and now we can make the summations to write z. So we are in this at this point we are trying to reconstruct z. So we have these sums for the second order terms. There are many terms like that, and then the second order term can be summed up so that we get finally the expression that we have seen. This is the expression that we get at the end. We can show this if you want to see. We just make it appear by changing here. Users of Maple know that. And see, this is the r squared. The term in delta r squared is here. Note that we have r over 4 multiplied by the second derivative of r with respect to the radius. The term in theta, second order here, r over 4 again, and dr with respect to r multiplied by r. This term is just this one. And the second order derivative of r with respect to theta, which is here. And the others are just like that. Let's just put this to get a cleaner video. Notice that we are also applying the equation to ZQ here, okay? So we have also the result of applying the ZQ to the equation. Now we will reconstruct our terms, zero order, dr in first order, g theta in first order, and d phi in first order, to show that we do get these two terms. Notice that this is not the demonstration yet. We are only showing in the next steps that these two terms are obtained. For the first order, which is here, we may compare what we get and this term written directly. They must be 0, so we got 0. That is to say, the term coming from the application of the characteristic function into the equation and taking the zero order term gives exactly this equation here. This is what we have here. We are writing this equation explicitly here, which is here, and the zeroth is coming from the application of the equation on the here on the characteristic function. So in fact we are proving that this is the term we get. We can make the same steps for all these terms and compare, of course. So they must also give 0 if they are right. This is good. We get 0. And now we have these two equations, and we must show that these two equations come naturally from the Schrödinger equation when we substitute in it the this expression for the psi. So we write the Hamiltonian operator for written in spherical coordinates. This is, we are assuming that the potential is depending on only on r, but this is irrelevant for the demonstration. We of course write C this way, and now we try to get these terms, but now from the Schrödinger equation itself. Okay, then we find the term there. Note we have it here, and now compare the term in dr, d theta, and d phi with the terms coming from the equation. That is, this is the term that comes from the application of the quantization method, and this is the term that comes from the use of this expression, the Schrödinger equation, and taking dr derived by with respect to r scalar. So this also must be zero if we have the correct result. So I'm not sure I have passed here. Let me calculate again. So let's see, this is all zero. This means that the Schrödinger equation, when we perform the necessary algebraic calculations, give exactly these two equations here in the desired coordinate system, which is the result we want to present. But before going out from Maple, I think it will be instructive to present you with uh, what is behind Maple, and it's not shown because I'm using this kind of operator that hide the result, the written result. Here I will show you the size of the calculation that comes when we substitute the characteristic function, which is here, in the equation for the characteristic function. And just for as a way to appreciate this, look at the bar here when I put Maple to show the results. Look what happens here. Maple is then calculating. I expect that. Not sure. This is. Look at here. Look the extent of the calculations. You see? This is what we get when we do the substitution of the characteristic function in its equation. So it's far from being a trivial result. Although the algebraic calculations are simple, we just make derivatives and sums and products. There is nothing very difficult with that. It can not be assumed as a coincidence that we end up with these three results here, together with the 0 or 1. So I hope you find this as an indication, a very hard indication that the quantization method is very sound. So now let's go back to our presentation. So we get back to the presentation, and what we see, this is important because it is possible to show. I will not go into this here, but it's possible to show that quantum mechanics, in the way it's derived, is always invariant with respect to Mathieu canonical transformation, but I won't go into this. And what we get here is to show that the same method that gets us the Schrödinger equation in Cartesian coordinates can be can be reproduced to let us get the Schrödinger equation written in any curvilinear coordinate system. In the next video, we will be talking about the Bohr-Sommerfeld rules. We will show that these rules are a special case of the our derivation method. So they will be derived and not just imposed. Thank you for watching.